I'm Niko Kurtti from Shopify. I work as a production engineering in our cloud platform team. And today I'm hopefully telling you something interesting about the platform we built internally for our developers. So to get us started, how many in the audience knows the company Shopify? Or knows that have used Shopify's products in some way? OK, a few hands. It's actually interesting that we host a really big portion, especially in the US market, of all the e-commerce stuff that is around there. So we are a Canadian e-commerce company. On the e-commerce sites that you might have used, like, for example, if you are into Kubernetes like I am, if you bought the Kubernetes hoodie from the CNCF store, that's hosted on our platform. So if you buy a Kubernetes hoodie, you are actually buying it on a Kubernetes platform. So we do stuff like that. We have a wide range of merchant sizes. Some of them are small, just getting started in the world of commerce. And some of them are huge, like Kylie Cosmetics or something like that, are like a multi-million-dollar business. And yeah, right now we have over 3,000 employees. Last year we processed about 26 billion in terms of sales. On our platform, we have over 600,000 merchants. And during peak hours, we do about 80,000 requests per second. So that should give you a good idea of the size and kind of the scope that we are doing internally. So to get us started on this journey, we have to jump back into 2016. So in 2016, we lost the great artist David Bowie. But on a more positive note, Shopify was gaining traction. We were growing like crazy, and things were really going well for us. We were running services in various places. So this is the thing that happens with growth, right? So you have something in one place, you grow, you start putting stuff into other places, and eventually you might end up with a sort of a spaghetti environment. So that's kind of where we ended up. We had our own data centers where we were using Chef and Docker. Then we had a PCI environment that wasn't using Docker. Then in addition to that, we had a separate AWS environment where we were using Chef, but we might be using Docker, we might be using something else. It was kind of messy, and it was based on whoever set it up and which time, like, did they set it up in 2014? Did they set it up in 2016? The difference was quite huge. In addition to that, we also let our developers use Heroku. So we had a corporate account that everybody had access to. And that was a really efficient way for our developers to get started on new projects, prototypes, whatever. Like, they didn't have to wait for any kind of operations team to help them get started to spin up environment. They could just use Heroku as they would on their hobby projects. Or if they came from another company, they might have already been familiar with Heroku. In addition to that, we also introduced a new concept called service tiering. So we have 4 different tiers that each application belongs to. The higher you are in the tiering system, so if you are tier 1 service, let's say Shopify Core, our main monolith, you are on tier 1. If you are on tier 2, you might be something like our fraud detection system. So tier 2 is kind of really crucial for our platform, but something that can be down and people can still use our services. So it's not like Shopify is down essentially, but it's still impacting us in a really bad way. Tier 3, tier 4. Tier 3 is usually internal services. Tier 4 is prototypes, hack day applications, stuff like that. Higher you go on the tiering system, the higher our service level objectives are. But at the same time, the more we also require from those applications and teams. So for example, tier 1 has to have regional redundancy, incident response drilling, stuff like that. And the lower you go, we require all the lower tier requirements, but the lower you go, the least is expected from your service. This model wasn't scalable. We had this problem of having these random environments really artisanally set up by different people. At the same time, we were trying to add this process into the mix. So we were trying to get a really nice way of tiering these applications. And the things that we found not to be scaling is any kind of manual or artisanal process. So for example, we were using Chef, but because all the environments kind of look different, we had tons of cookbooks, we had tons of different things that were working kind of differently. And in addition to that, in some cases, like people that are familiar with Chef or Puppet or any configuration management tool knows that they are somewhat brittle. So for example, I remember back in 2016, it was a common pattern in our playbooks that if a bootstrapping Chef run doesn't succeed, you just run it again. It will most likely work on the second try. But you have to manually trigger that second run. Any kind of slow things, processes that make people wait, Obviously, Heroku was one answer to this, so people didn't have to wait for operations team or anything like that. Rusty/wobbly thing, so again, going back to all the problems we had with our configuration management tools and all the problems that everybody has with their configuration management tools usually. They work in the happy case, they work in the time that they were created, but a little bit later they might be broken due to updated packages, updated use cases, someone made a change in production, and the change caused a bootstrapping mechanism to fail or whatever else that might be. The things that we knew how to fix this, so we knew that we needed to add more testing into our infrastructure. We knew that we need to add more effort into automation. What we wanted to keep is give our developers a self-serve system, but also create some safety guards around it. So giving people access to Heroku, for example, works great for the self-service aspect, but it doesn't work so great for thinking about security and giving those guardrails to people, essentially. And also, we were making big changes in our products and engineering teams. So previously, we had a really traditional operations team, which was kind of responsible for everything. Everybody was on call for the whole platform. We were chasing this model in the way where we had a production engineering team as the kind of the parent of everything, but we had sub-teams that were specializing into specific portions. So for example, I belong to cloud platform team. We have a data stores team that deals with MySQL. We have a team that focuses on developer acceleration, so creates tooling for our developers and stuff like that. So that really gives production engineers the possibility to go deep into the expertise that they know about. And if I could get the clicker work. There we go. So we started on journey to build a platform as a service. We had this really good idea to have one single platform that would fulfill all the stories for how do we build stuff, how do we run stuff, and how do we deploy stuff. So this quote for Lord of the Rings really rings bells because this is exactly what we wanted to do. Bring all those services, bring those applications into a single platform that we control. When we started designing this platform, we had three big principles. The first principle was that it has to be a paved road. So we didn't want to introduce that wobbliness and kind of flakiness into this platform that we had with our previous configuration management tool. We didn't want to expose that problematic cases to our developers. We wanted it to be a smooth experience, something like they would experience on Heroku, for example, to our developers. In addition to that, a paved road is also usually a fresh road. So what that means is that we had the opportunity to kind of pick our type of tarmac, so to speak. So we knew the use case that we were running on this tarmac. So for us, it's mostly Rails and also Golang. So those are the two technologies we wanted to really target with this platform. And a third and a big thing is also the security aspect. So again, giving developers the freedom, but also giving them a little bit of guardrails around this road so that they don't crash in the first corner. Second principle was hiding complexity. So we knew that any platform that we are going to be creating is going to be complex by nature. We are dealing with distributed systems. We are dealing with a really large problem scenario, really large problem domain. So we are talking about building deployments, all that stuff. It's going to be really complex, right? So we wanted to make so that the developers don't have to suffer that cognitive overload. And we wanted to create good abstractions and patterns that everybody could leverage. A good thing about creating patterns and abstractions is also that you share all the good practices that you've created for a single application. So for us, for example, Shopify Core, which is our main monolith running basically the core of our e-commerce site, we had tuned it over the years. We've done really great work in there. But the things that we've done in there in terms of like resiliency patterns just didn't go back to the other applications, the smaller applications. And as the company grew, those small applications actually became quite large applications. Obviously, they weren't the size of Shopify Core, but they were still large in the grand scheme of things. The third thing is that we wanted it to be self-serve. So again, people don't like creating issues. People don't like creating tickets. In general, people don't like interacting with people. So if you can interact with the computer, if you can make the computer do the stuff for you, that's usually better than going and asking somebody else to do it for you. It's also faster, more efficient, all that good stuff. So that was a big thing for us, that it needs to be a self-serve. We don't want to hire people to kind of be the cashiers of our platform. So now that we have those 3 big principles, we went into building mode. When you start building a house or building anything, basically, you need a good, solid foundation. For us, the foundation is Kubernetes. We looked into Swarm, we looked into Mesos, we looked into Nomad, we looked into basically everything that was out there for container schedulers. Kubernetes was picked because it had the best traction of the open source projects in start of 2016. It was platform agnostic, so we were still running in our data centers, we were still running on the cloud, so we wanted something that we could take anywhere and run it there without any kind of vendor locking into specific cloud provider or even operating system. We wanted it to be really general so we could make the decisions around everything else ourselves. Kubernetes was also one of the most extendable solutions, and it was written in Golang, which we had experience with. So we knew that if and when we need to go in and figure something out, or even fix something or extend something, we knew that we had the expertise inside our company. And in 2016, our prototype Kubernetes project actually started as a Hack Days project. So inside 2 days, we tried to get Shopify Core, our main monolith, running on Kubernetes. But we didn't want to spend time on setting up the clusters or figuring out all the bits and parts that goes into setting up a cluster. So we chose Google as the platform to do that. So we could get the Kubernetes cluster for free, well, free as in terms of engineering time, and we could get started and went into the actual business case of getting our application running there. And that prototype ended up being a huge success. We got good experiences from what we need to fix and what worked really well in there, and we were really happy with what we saw in those 2 days. So now that we have our foundation, the next thing is that you need something on top of the foundation. So again, we didn't want to reveal Kubernetes to our developers. That would be way too much complexity for them. That's not their daily job. Their daily job is to write software, write new applications, features, and our job is to kind of offer them the platform to do that. So the building blocks you need to build a running an application. You need to specify your application's runtime. You need to build your applications. You need to deploy your application. And also, you need to set up your dependencies. So by dependencies, I don't mean like gem files or anything like that goes into your application. I mean, you might need SSL. You might need DNS records of some sort. So if you're a web company like we are, those are the things that you need to be able to actually run your application, have a public endpoint that people can actually use and enjoy. So to get us started, for us, creating an application runtime, we extended an existing application called Services DB. Services DB is an application catalog. So it's just a simple web UI of listing all applications, the teams they belong to, all that metadata that goes into application. But we extended it in a way where people can now also create environments in there. And the other part of creating the application environment is also setting it up on the Kubernetes side. For this, we opted to create a small Golang application that runs in all of our clusters and listens to Services DB calls and creates the Kubernetes namespace for this application, creates encryption keys, service accounts, whatever goes into kind of creating the scaffolding for the application's runtime. So here's a good quick example of how that works out. So in the top left corner, we have Services DB. The user, which in this case is, again, developer, just clicks Create Cloud Runtime button, and then he gets a list of like when it's going to expire, what's my stack, what kind of plugins / add-ons do I need. So for example, do I need Cloud SQL? Do I need Elasticsearch? Do I need Redis? Do I need, for example, SendGrid API keys to be able to send out email? They click those, and the end result is going to be a PR into the repo, which is vanilla Kubernetes templates. But we fulfill all those templates for the developers. So we still kind of expect them to read them. We expect them to understand the values. So for example, your web UI, like your URL, like we expect them to make sure that that's the correct one and stuff like that. We don't expect them to understand and how to read Kubernetes deployments otherwise. So now that the runtime is ready, the next step is going to be building those applications. So we were really happy with how people got started on Heroku, and we opted out to actually leverage Heroku-ish, which is an open source project to kind of mimic the same behavior that Heroku has. So our developers don't have to specify any kind of Docker file. They don't have to figure out how to basically say what their dependencies is. Heroku is really good in detecting that is this a Rails application. If it's a Rails application, I need to do a bundle install. I need to do this and that. And we also, in this case, opted to build a custom agent that does all this. It's running on our, well, it used to run on our CI environment, and we still leverage Build Guide, which is a CI tool close to something like Jenkins. But it has its own machines right now building those images and stuff like that. We actually have 3 separate build pipelines right now. So the main one, again, is Heroku-ish. The second one is Dockerfile, because for system dependencies, like let's say Nginx or any kind of like infrastructure side dependencies, Dockerfile is still the better way to go than Heroku-ish, because Heroku-ish has no idea how to build Nginx, for example. We build about 500,000 images each weekday. We have 500,000 images in our registry, and we build a little bit less than 10,000 images per day, I think, on workdays right now. So that should give you a good idea of how much this system is actually used. Next bit is deploying your application. So for us, it's called Kubernetes Deploy. Again, a custom tool that we just had to build. The reason was that there was nothing good that would give us kind of the normal deploy workflow of having a synchronous, you start deploy here, and it either succeeded or failed kind of thing. So we already had an existing open source tool called Shipit, which is a web UI for basically running commands. And we used to run Capistrano commands in there, and it's a good web UI to see what's happening, what ends up where, and what is the end result. This replaces the Capistrano in that piece. It's basically a pass-fail result thingy. So it does a kubectl apply underneath. So it applies the templates to the Kubernetes cluster. But after that, it starts polling the Kubernetes cluster to figure out that did all the deployments went through? Did all the replicas come up? And if there's any kind of failure, like, for example, somebody does a typo or some configuration map is missing or whatever, we try to show that error as clearly as possible. So for example, we have a little bit of logic for figuring out and showing the failed containers logs automatically as part of the deploy. It also has some other helpful stuff like having a pre-deploy for configuration maps and secrets. So again, like to avoid the egg chicken problem of your application relying on a configuration map, but you haven't deployed it yet, we have this pre-deploy system for certain resource types. It also has a little bit of protection mechanisms in terms of namespaces, and it also does a kubectl prune, so it deletes everything that wasn't part of the deployment. But part of that prune is that we can also create safety mechanism for certain types of resources. And it's highly pluggable. So Kubernetes deploy is written in Ruby. It's a Ruby gem you can take. You can run it on command line on your local machine, like you can see on the right in here. But it's also like you can put it on the Jenkins, obviously. Like whatever tool you use to run any command is where you can plug this in. So it's highly reusable. And again, it's open source tool. So if you're interested in this kind of stuff, please check it out. And final piece are those dependencies. So for us, this is a framework called Cloud Buddies. What Cloud Buddies does is there's a body for creating DNS records. There's a body for fetching SSL certificates from Let's Encrypt. There's buddies for creating buckets, databases, services. Again, thinking about creating those abstractions so that either the thing is automated and developers don't even have to care. For example, DNS records and SSL records are that kind of stuff. Or they use some sort of abstraction to ask for buckets, and we set up the security rules. We set up the correct project for them, all that kind of stuff. In addition to that, Cloud Buddies are responsible for infrastructure stuff. So they set up quotas, they set up security rules, and lately we've also had to be creating a Cloud Buddy called Node Buddy. And what Node Buddy does is it detects bad nodes and it automatically deletes them. This is a screenshot from a while ago. We have 20 cloud buddies right now, and you can kind of guess from these names what they are responsible for. So there's like Pingdom Shop buddy, Airbag buddy, Redis buddy, Search buddy, which is responsible for creating Elasticsearch clusters. So it's a really nice system, and a really big thing about these is that originally, when we started out, we needed to create this kind of MVP/prototype, and we were creating a bunch of these buddies ourselves. For example, Cloud SQL buddy is written by the Cloud Platform team. But right now, we are moving into a place where all our sub-teams, like let's say the data stores teams, takes ownership over Cloud SQL buddy. Our security team has taken over our back buddy. So each of our sub-teams are also experts in their own context. Here's an example of the name buddy flow. So name buddy and all the buddies are just Kubernetes controllers. And what they do is that they talk to the Kubernetes API, and they ask for what's happening in the cluster. Is there a new resource created? So for example, in the case of name buddy, it listens to ingress objects being created, updated, or deleted. And it looks at the spec that can be seen on the left. And if there's hosts specified, it creates a DNS record that matches the ingress's IP, and it matches the host fields that are generated. You can see the generated DNS record there on the bottom left. This is actually a little bit more complex because we've had to do a little bit abstraction in here. But the basic flow that I show here is something you can write in, I want to say, 100 lines of Go. That was probably our first version of this. And it's a really nice way of like not just thinking about infrastructure as something really different and custom from all the other applications, but this is just an application that talks to two APIs. So your first API is Kubernetes, your second API is whatever DNS provider you use and their API. So this is no different from writing any other application. This has nothing specific to infrastructure rather than the domain of the problem is infrastructure. If everything went well, this is what our developers should be seeing. A service with SSL enabled, DNS automatically created. If they are using, for example, database on the back end, that should be auto-generated for them. Everything just should automatically be there, and they don't have to care about setting up all those dependencies. I want to talk a little bit more about our buddies, because this is, for me, especially the most exciting thing about Kubernetes and working with Kubernetes. So it's all about extending Kubernetes. So Kubernetes APIs, at least in my experience, are very well documented. So it's really easy to get started. There's a lot of like blog posts. There's many ways to get started. And if you know how to use Google, you will be on your way in like 15 minutes. The client libraries are really high quality, at least on the Go side. I've also used a little bit of the Ruby libraries. Both of them are really high quality compared to something I've worked before that. And what this gives you is the ability to not only hook into the existing concepts, like I hooked into ingress objects in the name body, but it also creates the possibility of creating your own data type. So if you are familiar, and you probably are familiar with object-oriented programming, you can think about all these objects as just being what you can create dynamically into the system. So there's no custom DSL or anything like that what you work with. You just work with your own object types or the built-in object types. Also, a big thing that you get out of these libraries are distributed system primitives. So you get stuff like leader election and latches and all that good stuff for free. So you don't have to worry about it. You just leverage what Kubernetes already knows how to do. One thing that we haven't done yet, but I would be excited to see, is using these offerings in an application that has nothing to do with infrastructure. There's no limit if your application is dealing with infrastructure, if it's dealing with Kubernetes, or if it's doing something else, but it needs leader election for something else. So it's a really nice way of not only creating these abstractions for your infrastructure, but also leveraging the primitives for any other application that just happens to run on Kubernetes. And again, they are just Golang applications, so unit testing you can do as you would normally do. They are run and deployed as normal applications. There's nothing special about them. There's nothing custom or special to Kubernetes. And the TLDR, how you write this, is you want to get to a specified state, a desired state. That might come from somebody updating a template and applying it against the cluster. That might come from from a new object being created, whatever the case is, you compare that to the current state, and if those states don't match up, you reconcile. That sounds simple, right? And that's usually what you end up doing. So only thing you have to do is authenticate against the cluster. So again, it's just an API. You create a watcher for the type you are interested in. You create those functions to do what you want to do. So it might be you want to internally do something like, let's say, Redis Buddy, for example. It creates Redis deployments inside the cluster. But it can also be talking to, let's say, in our case, SendGrid API to fetch those API keys, or it can talk to DNS provider API to create those DNS records. Whatever the case might be, it's always this kind of same flow. How do you do it? And extending those object types. So custom resource definitions is how you do it in Kubernetes. We've really heavily used these, and we really like them because that's exactly the kind of abstraction we wanted to offer our developers. They don't want to deal with hundreds of lines of deployments and services and all that. For example, if you want to create an Elasticsearch cluster of 3 nodes even, that would be a really verbose YAML setup. For us, we can abstract all those things. We can offer them a simple template that they can understand. They only need to understand the variables. And all that logic, all that complexity is hidden inside the controllers. Again, sharing those patterns, hiding that complexity, not putting that cognitive overload on your developers. Huge thing, huge thing. And again, they consume configuration parameters, and it works similarly to what the built-in object types work. So there's no difference. If you look into Kubernetes proper, how they deal with deployments or services, there's no different on how you would write your own controllers if you would be doing the same thing. This is a really big thing because you can look at inspiration in Kubernetes proper, but also you know how the system works underneath, and you can understand from writing your own stuff on how the Kubernetes proper also works. Here's an example of, I think this is taken from Kubernetes, like getting started on Kubernetes or something like that. So there's a deployment object. It's setting up an Nginx with 3 replicas. You can see in the spec that there's spec has all the variables that the developers would care about in this case. So there's one container type. Its name is Nginx. It uses specified Nginx image. It opens up a certain port, and that's about it. Now let's look at our Elasticsearch CRD. You can see the same thing. The kind is Elasticsearch. Don't mind the ERP syntax, but you can see the same thing in the spec. So Elasticsearch version 6, that's what they care about. What version am I running? If they change it to, let's say, if there's a 7 release, we would create that logic inside our own controller to do graceful upgrades for them. What zones does it run in? What kind of nodes do we want in that cluster? How many nodes do we want in that cluster? What bucket do we use for backups and stuff like that? This is all very easy to understand, even if you have 0 idea of how Kubernetes works or what even like these templates mean. You can still understand all the variables quite well and change the things that you care about. Supporting our users. So when the automation fails or when there's a new use case that you haven't covered in your platform. For us, we had to create a custom cloud portal tool. This is basically the tool that bridges the Kubernetes world to the abstractions we want to offer them. So Cloud Portal is kind of a kubectl limited on web UI. They can do stuff like restart ports, look into ports, look at their ingress IPs. Basically, all the basic operations you can do with kubectl, they can do here. And we scope them by namespaces, so they can only access the applications they are supposed to be touching. The great thing about web UIs is that, again, you don't want to introduce that complexity to developers. So when you go into a web UI, you can just click around and find the stuff that you are interested in, or find stuff that you didn't even know you wanted to know about, but it's there visible. While if you offer kubectl to your developers, they actually have to know what they're looking for. They actually have to read Kubernetes documentation, figure out what's a service, what's a deployment, what does it mean, what's a port, and all that. In here, it's kind of a cheat where you just click around and you kind of start understanding what the things are by looking at the names and stuff like that. This has been hugely popular inside the company. There is a minority of people that still likes command line tooling, and we are looking into actually offering kubectl to our developers, those that are a little bit more advanced or just want to know how things went underneath. But this does like more than 90% of the things that they want to do. Like Another big thing we did was documentation, and documentation in a way where we didn't want to document what we did and how the system works underneath. This is not a manual on how to fix the engine. This is a manual on how to drive the car. So you can see in the glossary here, there's stuff like understanding deploys, setting up your application, viewing logs, job workers, web workers. So this is more to ask the questions of how do I do X on this platform? And you can go here and you can probably find the answer to that. This is not a manual on how does Kubernetes deployments work or how does Kubernetes rolling deploys work. This is more about how do I make thing X happen for me from developer perspective. And when documentation and automation fails, you still need the support system. For us, I want to point this out because this is a little bit special. The first time I've seen this in my professional career is that we have a large-ish support organization at Shopify, and we were able to pull a person from that support organization to support our cloud platform. She's Jenna, and she's been awesome. Like, she's expert in supporting users, knowing how to talk to users, knowing how to collect important data to bring back to the developers, in this case, me and my team. And it's been a huge success. It works so much better than having developers on call answering questions like, how do I do X, how do I do Y? Usually works out just fine, but it's just a different kind of mindset when you have people that are interested in supporting people, interested in gathering that kind of data and stuff like that. We still have a secondary on-call rotation where somebody from the cloud platform team is kind of the expert that Jenna leans onto. So if there's a specialty question, if there's something really new Jenna doesn't know, there's always somebody that she can go and ask, and that person's time is reserved for helping Jenna. So how have we done so far? So again, we started in 2016 Q1. We are now in 2018. We had our first users on the platform end of 2016. So we've had a year-ish plus of real developer usage. The turnaround time to getting an application running on cloud platform is unreal. You folks have really nailed it. Positive feedback like this feels really good, right? And I'm not bragging in here, although I've been part of building this platform. But just getting this kind of positive feedback feels so nice. And I feel like we've really nailed the things that we wanted to do in here. On a more negative side, I kind of gathered from the feedback we've asked our developers internally what they find bad or lacking or whatever. And these are the challenges we've kind of seen. So people are still kind of confused about how does deploys, builds, everything basically work. So coming from, let's say, Heroku, or coming from a traditional enterprise environment, they might be a little bit confused about where do I SSH for production, for example. There's no SSH to production. How do I scale? So again, like if they were on Heroku or AVS, they might be using autoscalers. How do I set that up in here? How do I pull that slider that's on the Heroku UI? How do I debug? So if there's a problem in production, how do I debug? How do I use strays? Stuff like that. And is this worth it? So again, developers are thinking about the features they are building, the new commerce stuff that we are building. They are not thinking about, am I running on Kubernetes? Am I running on this and that? They are mostly focused on, I want to build this feature that works for our merchants. And moving them to our platform, we took the approach of making the users do it themselves, because we also wanted to make sure that the pipeline is good for them. And the question that comes up is this worth it? Like, what am I gaining from this? Why would I move? And that's a really important thing you should pay attention to. You want to make sure that you don't force users to move to the new platform. You want to make sure that you have some things that you can bring to them, like, you can do X on this, you can do Y on this. This is going to be so much better when you move on to this. Like, you get this for free, you get that for free. This is going to be so fancy. And if you convince people that this is going to be a good thing for them, they are going to be your cheerleaders inside your company. They are going to be talking to other developers, other friends in other teams, like, this is the new cloud platform, it's so great, we are doing this and that. And then you don't even have to force anybody. Everybody wants to jump on your platform. And that's exactly what we ended up having to do, is that we had the beta, the beta went fine, and after that, people were really excited to kind of jump on the platform. Challenges for production engineers. So at the same time, we were moving from our data center focused land to cloud and giving more control on the underlying infrastructure, be it the bare metal host, be it the transit networks and stuff like that. Like we had our own routers, our IP space addresses, and all that good stuff. So for example, if customers in Germany were having issues, we could kind of pinpoint the traffic and figure out which transit we were using and move them to another transit. Now on Google or AWS, if there's a problem with customers in Germany, we have no control of how that traffic goes in there. So we have to kind of figure out new ways of working around problems like that. We were running containers since 2014, but we weren't using them everywhere. We were using them for stateless workloads. And container-only world and all the tooling around it is definitely something new to the people in the company. So for example, we are running stuff like Kafka and Elasticsearch on Kubernetes. We are running Splunk on Kubernetes. And there was a huge amount of effort that went into figuring out all the things that you have to think about when running those on containers and on Kubernetes. And constant pressure to migrate applications. So same as developers, our production engineering have certain goals. They have to scale to a certain amount. They have to figure out how to support certain new applications. At the same time, they had to migrate our own workloads, like our build systems and stuff like that, onto this new platform. And it's a constant pressure on, is this important enough to do now? What do I have to do? And in case of like infrastructure tooling, they are usually a little bit different than your vanilla Rails application. So there's a lot of things that go into figuring out how to run these things on the new platform. And just learning, like we hide that complexity from our developers, but we don't hide it from the SREs and production engineers. Like they have to know that complexity. They have to understand it. So there's a lot of things to take in when understanding something like this. Takeaways from all this for us is that when you get started building a new platform internally or externally, it doesn't really matter, don't try to cover all the edge cases. Target 80%, 90%, some percentage that you want that is less than 100, and try to make that a really smooth experience. That paved road again, like try to make that the smooth experience. After you get the initial user space, you can then think about all the edge cases, all the things that you have to still do, but especially for the MVP, just think about the specific good use case that you can build a good, happy path on, and yeah, build that. Create patterns and hide complexity. That's, again, really important thing. You don't want to overwhelm your developers and users by all that cognitive overload. You want to make sure that they feel comfortable with the new platform. They don't feel threatened by the new platform. They feel nice and excited about the new things. Educating, really big thing. Again, our documentation, we put a lot of effort. We pulled in technical writers inside our own company to help with that documentation. So it's high quality. It's not something that I wrote during my morning coffee when I actually wanted to write code. So we really put a lot of effort into making good documentation and education. And again, get people excited. So we did internal talks. We did all kind of things internally to tell people that, hey, this is going to be awesome. You can do all this kind of good stuff on here. If you move between teams, it's all going to be familiar to you. Everything works the same, no matter if you work on Shopify Core, which is our main monolith, thousands of nodes, or if you run your Hackdays applications that you just wrote while I was talking. No matter which one it is, it's going to work about the same. And last but not least is be conscious about vendor lock-in. So it's really nice to leverage things like Cloud SQL, RDS, and other services, or even like cloud-hosted Kubernetes. But be conscious about the things you want to log into. So for us, for example, the Kubernetes was one of the big choices just because we knew that we wouldn't be logging ourselves into any specific provider. Again, we are using Google right now really heavily, but if we wanted to move to another cloud, and we are looking into multi-cloud, we can easily move the workloads around. We ran Kubernetes ourselves in the data center. There was no problems with that. Another thing that I think we did quite well, but we still end up building a lot, is internal vendor locking. So you get this, like not built here is a really big threat to you. So you don't build everything yourself. Try to leverage all those services, and at least be conscious about what you need to build internally, what you need to build, externally pull in, and can you buy it, can you cheat by buying it, or do you have to actually build something? Our future is really polishing our own tooling. So we built a bunch of this stuff inside our own cloud platform. We built the Cloud SQL Paddy and stuff like that, which now belongs to other sub-team. But there's a lot of rough edges that we need to kind of smooth out and make it better. And we are not even trying to be Heroku. We are trying to be kind of like if Heroku is a Toyota Camry, we want to be the race car. So we want to be really specified for our own use case, and that's where we want to specialize, and that's where we want to do the polishing part. Another huge issue right now especially has been that we've hit limits with Kubernetes. So for example, I think official numbers for Kubernetes is that you can run thousands of nodes inside single cluster. You definitely can't unless there's nothing happening in that cluster. So for example, Shopify core is distributed among multiple clusters just because when we deploy the amount of load that we create on the API server just couldn't scale up. And we did look into the code base, we did look into optimizing etcd and all that, but there's no easy shortcut. So we've been kind of hitting these issues with Kubernetes where we need to figure out new and creative ways of working around all the scaling issues. Optimizing cost is a big thing. So we moved to the cloud with the idea of we want to create this platform and we will worry about the money later. Now we are at the point where we are starting to worry about the money. We are introducing tooling to kind of show each team how much their applications are costing. We don't even want to create an internal billing system or anything like that. But it's really nice for the teams to also understand that if they are running some sort of small application, do they actually need hundreds of replicas? Should they put effort into figuring out how to optimize their MySQL queries and stuff like that? Or should they just keep putting money in there and scaling up, for example, Cloud SQL instances of the amount of replicas? Multi-cloud, like I mentioned, we are right now running only on Google, but we are definitely looking into expanding this. Again, going back to all those traffic issues and all that kind of stuff, we want to make sure that we have a good story for working around whatever issue our providers have, so that we have a good fail-back, fail-over, whatever you want to call it, solution for stuff like that. Service mesh is also a big thing we are looking into. So as we've created more and more applications, and we are maybe in the thousands, I want to say, in the applications right now, we want to make sure that the communication between these applications is secure, and we have good insights into how they are discussing between themselves. Again, coming from the data center focused land where everything is in an internal network and everything can just talk to each other, putting it on the cloud and figuring out talking over public internet is a totally different thing. And that's still something that we are working on. Thank you.
So I think we have a couple minutes for questions. Does anybody want to start with questions?
Yeah, I was wondering what criteria you use to set up your clusters. Like, why not have everything in one cluster? What criteria you use to divide up these clusters?
Yeah, so originally we started with one cluster per tier. Then we outgrew the number of nodes that we can put inside the cluster. Well, not necessarily amount of nodes, but let's say the amount of operations we can do in there. So again, Shopify core needs X amount of nodes. And if you try to do a deploy in a single cluster, you just can't do it. So right now, it's kind of a mix of having n clusters per tier, and we deploy those applications in those n clusters per tier. So that was the earlier thing. Let's see if I can show it quickly. So we classify all our applications into 4 buckets. So each application belongs to a single bucket, and it's based on the priority and their SLOs. So for example, our Hackdays applications go into tier 4 clusters. Tier 2 clusters, we have fraud detection and stuff like that. So that's how we separate them.
Other questions?
Thanks. Thanks for your talk. My question is about unexpected consequences of making something abstract and simple. Just like when we first started using Hibernate, I remember like everything just worked for you, and then later on you realize, oh wait, there are these like terrible queries that are taking forever. I wonder if you have any war stories about things that people unexpectedly and unintendedly do now that there are layers of abstraction between them and what's really going on.
Yeah, that's a really good question. So the question was mainly about creating those abstractions and making sure they don't backfire on you. For us, it's been a constant dialogue inside the team. Originally, we had people on the team that were really strict about, like, they wanted to reveal all the Kubernetes internals for our developers, and then there was the other people that wanted to create an internal version of Heroku, essentially, and hide basically everything. Right now, we are in the mix of those two. we haven't seen any big problems with this. It's usually more about, like, for example, Cloud SQL supports both MySQL and Postgres. Internally, we don't really use Postgres, but there's been a few use cases where some specific application really needs Postgres for a certain specific feature, and we just don't support it in our abstraction layer, although the underlying Cloud SQL would support it. And in those cases, we had to make the decision of, hey, this is not a priority for us. We just can't support this right now. We can instruct you how to work around it, or we can start building that feature at some point of time. But it's usually those lacking features rather than something blowing up on us that we hit into with these abstractions.
Any other questions? All right, well, I'll let you know if you're staying with us in the track that we're going to move to, I think, Times Square room on the 7th floor for our open area, so you can come and interact with a lot of the speakers, interact with each other, and learn about other things in this space. So thank you, Niko, for presenting.
Thank you.